Get out of here. Get. Oh, God, I cannot believe I knew this would happen. I don't know if you folks have heard, I think I mentioned it last time, but apparently we got birds. Birds have gotten into the learning center. We can't get them out. They're in here. Hopefully they'll find their way out however they got in, maybe when people come back. Hopefully sooner than later, right? But for now, just call someone if I get attacked, right? If I stop moving, all right? But hopefully they won't bother me. Hopefully they won't bother us too much. All right, anyway, when I'm not dealing with birds, apparently, maybe I'll get a cat. I just want to invite you back to the second hour of our 45-hour lecture series of PChem 2. We're still on Maxwell-Boltzmann. We will be for this week and next. Remember that this is mostly in that chapter of that textbook that I'm writing myself. It's not enough for the entire semester, but this part's in there. For some reason, it's not in the textbook that you were assigned last semester, and I didn't want you to have to buy a new textbook, so that's why I'm doing it like this. I know it's a little awkward. I know my textbook is a little rough, right? It's a first draft. Regardless, in Maxwell-Boltzmann, what we're doing today and through next week, it's all based on probability, and it's a good warm-up for quantum mechanics, which is also it's a mathematical paradigm based on probability. And what we're trying to do is to use probability, the mathematics of probability, to calculate properties of molecules. And part of that is, now last time I talked about Kb, which is the Boltzmann constant, which is just the gas constant R divided by Avogadro's number. It's the gas constant for a single molecule. So kBt is the energy of a single molecule by virtue of it having some temperature. Let's say everything's at room temperature. That kind of makes sense. And so I try to, the whole class, I'm going to try to talk about a single molecule, and based on the properties of that molecule, what would be the properties of, say, a gas of that molecule. Like, for example, what we're going to be able to do by next week is by analyzing, remember this is the Boltzmann equation, by analyzing the Boltzmann equation, you can tell me about a molecule, say a molecule of O2, and I could then tell you what the pressure is of O2 at room temperature. So that's the kind of thing that this class teaches. So that's kind of remarkable, right? That's kind of neat. And you're also going to learn a little bit of deeper mathematics as well. Now, another thing I like to do, this being our second class, is I tend to spend a fair amount of time reviewing whatever we did last hour. And part of me sometimes thinks that's a waste of time, but what influences me is when I had this class, that's what the guy did. And I was always surprised how much, like from Monday to Wednesday, how much I forgot about, like what was the thing that we left off of. I'm surprised. I usually just totally forgot. So anyway, so I'm going to spend a good 5 or 10 minutes reviewing what we did the last hour, and I hope that's helpful. Most people have said it was, so we're going to stick with that. And other news is, I guess, just remember your homework assignment is up, so that's due in exactly 1 week. Just make sure you send us a good scan, and I guess I don't have any other class business as long as those birds stay away. So let's go ahead and start reviewing again. I've kind of been reviewing a little bit, but let me back up a bit. We talked about Boltzmann distribution last time, but let me remind you what that's the probability distribution for how nature doles out energy to molecules. Now, by itself, that probably doesn't make any sense, but as we work with it in this hour, it's going to start to make more sense. But let me back up a little bit. Let me back up a step from there. Remind you what do you do with a probability distribution? Probability distributions are not useful unless, let's say that's a probability distribution of energy. It's not useful unless it's integrated, right? Because what you do is you take a probability distribution, you multiply it by a spread. We talked about spreads last time, like when I was flipping a coin. You can't ask whether like a mole of coins is exactly 50% heads, 50% tails. That's complete nonsense, because that will never be true. Remember in our let me give you a more specific example. For 1,000,000 coins, if you flip 1,000,000 coins, it's almost impossible for exactly half to be heads and half to be tails. So you have to have a spread The spread is quite small, and again, look at last lecture, that table, and I showed you as the number of coins increases, the spread decreases till it becomes a partial, especially if you're talking about a mole of coins. Partials, no problem with partials, but whenever you multiply your probability distribution times a partial, you're going to have to integrate it. You have to, otherwise it's meaningless. Okay, what do you get? You get probability. This is a probability distribution. It's integrated to probability. Probability is exactly what you knew since middle school or probably elementary school, that the flip of a coin is 50-50. Now that you understand. And this is what we're working on. Recall also the property of normalization. If we integrate over all values and your limits are going to be based on, remember that they have units, and the limits are based on the partial. So I am integrating from a lower to an upper energy because the partial is energy. The lowest energy you could have would be 0, and the highest energy you could have would be infinity, joules, because we're in SI, and the probability that a molecule either has or does not have energy is 100%, which is 1. Okay, so again, just reviewing. Now you know what? I was going a little fast last time and I talked a little too long, so I have a little bit of time. So let me show you what I'm going to have on homeworks and exams. Because we're going to be talking about velocities of molecules, and there's a couple other tricks we have with Boltzmann distributions. But I don't know that that's really useful. Instead, what I'll do on tests is I will work questions that are perhaps more relevant. Like, all right, so this is PChem for biochemists. So I'll say, what is the probability that a patient is in a hospital? Or what's the probability that a person is diagnosed with Alzheimer's? Stuff that you might care about a little bit more. The mathematics is all exactly the same. I can either integrate over energies or integrate number of patients. I mean, it doesn't matter to me. What's important to you is that you have some intuitive sense that how these works, and that, as a college graduate, you're not stuck with thinking about probabilities and average values as though you were in middle school, right? No, we're not going to do that. All right, so let me give you an example. Now let me be silly with this, because why not? What if I was asked about the average number of kitties in a house, all right? So, here's kitties, integrate kitties. And you see, I can get real crazy with this stuff, right? But you have to know what you're doing, because you can't just memorize whenever we come up with what we do in class, because I can come up with anything on a test. Okay, so I've asked you to do this. Now let me throw you another monkey wrench, because I'm going to do this. I'm going to give you a problem and a solution, and I've done it incorrectly. I do this a lot, because answering questions correctly, it's not that hard. The average of this class tends to be pretty high, tends to be around 80%. So for the most part, you're answering questions correctly. Cool. I do appreciate that. However, when you're on the job market, or okay, you all want to be doctors, right? So a patient comes in, if they're perfectly healthy, there's nothing for you to do, and to be blunt, you're kind of useless. You need to identify what's wrong. Am I correct about that? Yeah. You need to fix problems. Problems occur because something has gone wrong. So what I do is I work problems. There's a section on the test where there are problems that have already been worked, but worked incorrectly. And you have to identify what's incorrect. So you really got to know what you're doing. You can't be memorizing stuff. That ain't going to work for this. So let me give you an example. So I'm integrating kitties. I've integrated from minus infinity to infinity, and I get 0.5. Okay, and the question says, well, what's wrong with that? Okay, probably because you should have gotten 1.0, right? It's not normalized. So what's wrong? Right? You should, if you're integrating a probability distribution, any type of probability distribution, so you notice I'm just kind of throwing you off by making it cats. That doesn't mean anything. You should get 1.0. So what's wrong with this equation? And the answer is, you can't have negative infinity kitties. You can only have the lower limit of number of kitties would be 0. There's no such thing as a negative cat. And if you do that, I would also set up the problem that you could actually verify that the answer would be 1.0. Anyway, that's the kind of questions I ask on tests. I know I've wasted a ton of time, but I just wanted to throw that out to you so that you get used to that, because that's about a third of the test are questions of that nature. Okay, well, let's get rid of this kitty stuff. And so we've talked about what you do with probability distributions. You integrate them into probabilities, and this is the Boltzmann equation. Okay, so what's next? What's next is to identify the energy of what? I've kind of given you a hint here, but let's pretend you didn't see that. Oh, here. Oh, little wiggles like that just means I'm talking about something else, by the way, when I do that. Okay, energy of what? So, what type of energy? Okay, let me just rattle off a couple. You could have rotational energy, you could have vibrational energy, you could have translational energy. We're talking about gases, by the way, just because it's just easier. Let's see, you could have nuclear, both strong and weak nuclear force. Oh, we could have gravitational energy, that's a type of energy. I feel like I'm missing one. What am I missing? Anyway, look, that's plenty. All right, now here's the deal. The Boltzmann equation describes all of those things, but we need to pick one, and we're going to pick translational energy. So that's what we're going to do. It's because it's not that hard, and you can figure out exactly what you can do with the Boltzmann equation. You just have to pick one, right? So we're just going to pick translational energy, 1/2 mv squared. And again, with that, we can figure out all kinds of really interesting things. And the mathematics aren't that hard, right? And that's why we're doing it, because we're trying to build up our way to quantum, which the math is a little bit harder, right? So we're going to start easy. Okay, so translation. And here's a hint. I don't know if I mentioned this last time, but one of the things you can do with this is ask yourself, does a gas molecule move faster than the speed of sound? Right? Isn't that a good question? Like sound are pressure waves, and the speed of sound is like 700 meters per second, something like that. Can molecules move faster than that? Maxwell-Boltzmann, this thing we're doing now, can answer that question. And I bet you think no, and so I'm going to leave it at that. It makes sense to me the answer would be no, but we'll see in a minute what the answer is. Okay. So we're going to pick translation, and we'll not worry about those others. They don't actually matter for various reasons. I'll explain in a little bit. So if you plug in E as 1/2 mv squared into the Boltzmann equation, it's fairly straightforward. But note that the Boltzmann equation, this is really neat to me. The Boltzmann equation is for energy. It's how nature partitions energy. But if I plugged in 1/2 mv squared, I don't see energy. E is not there. V is there. So now it's a probability distribution of velocity. But it's still energy, but it's velocity. But it's energy, but it's velocity. See, it's two things at once. I don't know, I just thought that's kind of cool. All right, anyway. So now we plug in 1/2 mv squared. There you go. All right, now what? Okay, so there's a couple of things that we got to work on here that are a little bit tricky. Now, for one, this top part, minus mv squared over 2 kBt. M, kBt, those are constants. When we do these problems, I'll have to tell you the temperature, and it'll be room temperature. Okay, so that's a constant. Kb is a constant, mass. We're going to do argon. Argon's mass is, I don't know. It's something. Constants. Everything's a constant. So it looks like, really I've got like e to the minus x squared. Right? Now, the reason I'm saying that is that when we work problems, they're going to be calculus problems, because just for the reason I just mentioned. And I'm just going to assume that you have enough general knowledge of integrals that what I want you to do is to use some online resources. There's all kinds of websites that you can like plug in mathematical expressions and say integrate them, and they give you the answer. It's okay to use that. In fact, really, you're going to have to. And that's what I'm doing when I write the answers. You know, when I write the homeworks and the answer keys, I'm using those same resources. So you have to use them too. Isn't that cool? It is, but I also ask harder problems. But now hold on, that's fair. You're not actually going to have to do any of the integrals. All right, so I'm looking at this, and so this top part doesn't bother me too much. I can certainly plug in, go to a website, and type in e minus x squared, go, right? I'm sure probably a middle school student could do that. This bottom one, okay, this normalizer, right? This is like the business part, and this is like the normalization part of the probability distribution. What do I do with that? Yikes, that looks a little bit like, what? It's a sum? You know, okay, I see a sum and I'm wondering if like it's a Taylor series and Taylor series have limits. Okay, so this will not stand. I'm gonna have to basically do the sum and get some kind of other expression that represents the sum. Okay, now the way to go about that is, and again, remember this means I'm taking a break. One of the things you also have to remember when you're doing any kind of mathematical analysis of things that are real, you have to remember you work in 3 dimensions. You live in 3 dimensions. There has to be 3 dimensions in here. I have to be able to see x, y, and z, and if I can't, then I'm doing something wrong. Now, that's actually really quite easy because instead of v, I'll say v squared. V squared is vx squared plus vy, vy squared plus vz squared. Okay, x, y, z. Okay, cool. All right, so now I see my x, y, z, so I appreciate that. Okay, now I have e to v squared. All right, so I need one other identity, which is this. And I'll give you something that, like what I find on a Google search, e to the a plus b plus c, whatever, it doesn't matter, is e to the a times e to the b. Okay, and that looks a little bit easier. That looks easier than that, so I'm gonna work with that. Okay, so what? Am I ready to, yeah, let me go ahead and write all this out. And then I'm going to tell you a little bit more. So I'm going to expand this out in terms of Vx, Vy, and Vz. That's what I'm going to do. Now heads up. I'm going to write an equation that goes halfway across this board. Right, so start on the left side of your paper and you actually will be able to fit it in. There are times towards the middle of the class when we're doing quantity mechanics. Oh, that's awesome. Really? Okay. All right. I can't lower it all the way, it's annoying. Anyway, there are times where I'm going to write across the board twice, heads up. That'll be in about, really about 2 months. So anyway, I'm going to write once across the board. Okay, so P, okay. So this is a bit much. All right, here we go. Now at the top, told you, it's pretty big. Okay, the top part is not too bad. It's the same thing, e to the minus mv squared over 2 kbt. Okay, now I'm not going to put vx, vy, vz on the top part. I'm going to do it on the bottom part. And it'll make sense why I just need to write things down first, and then you'll see why I'm doing it. Okay, so what happens is when I plug in vx squared plus vy squared plus vz squared into the bottom part, the normalizer part, here's what you get. Okay, so we have vx and e to the minus mvx squared over 2 kbt. Okay, and then based on that identity, what you do is you just simply multiply. You just multiply the same, but instead of a vx, I got a vy. So right, it's not too bad. I'm just writing the same thing over and over again, just with a y and a z versus x. And I went over the line a little bit. So I'll just do that. Okay. All right. So the big picture, that what this identity here does is it turns this single sum into 3 sums, and each one is multiplied by the other. So not too bad. All right. One other detail. I think I mentioned this last time. When you're talking about velocity like in x, y, or z, we need to know like what we're summing over. And that probably sounds confusing, so let me just tell you what it is and then I'll explain it. What you're going to sum from is minus infinity meters per second. I won't write that down. To plus infinity. Okay. Now that's because when we're doing directional velocities, I understand positive velocities. That's easy. Negative velocities are for things going backward. Okay, not too hard. Now, remember that net velocity actually cannot be negative. So that it's kind of weird, right? Net velocity cannot be negative because of the formula. Net velocity is the square root of v squared plus vx squared plus vy squared plus vz squared. The square root means that you can never be negative. Okay, so just look out for that. That's actually going to come up in the test. Heads up. All right. Now that means that's the same for all of these. Okay, now the next thing that I was alluding to that may be like, what is, what are these sum? You know, summing what again? Summing from minus infinity to infinity. The problem is that sums tend to look like a plus b plus c plus d. And so what I'm doing is I'm plugging in different values of vx starting from minus infinity to infinity. But what are the individual terms, right? You know what I mean? Like, okay, minus 1,000, minus for vx, minus 999, minus 998 meters per second, minus 997. Is that what I'm summing? You know, what about minus 1,000 meters per second? What about 999.5 meters per second to 999 meters per second? What's the step size? That's what I'm trying to say. This sum means that I'm having to put in discrete values into Vx. So what are they, right? You know, from minus infinity to infinity. So am I adding, you know, when I'm summing them, is, you know, do I go like Vx is 0, plus Vx is 1, plus Vx is 2? Why not Vx is 0 to 0.1 to 0.2? Why not? Right? That's kind of confusing, isn't it? Here's the answer. And the answer is in quantum mechanics. All right. How am I going to describe this? All right. So here's how it works. I'm a gas molecule, and this room is a cage. It's a box. Okay. And I swear to God, this is true. Everything I'm about to tell you is true. And you're actually going to prove it in the first problem that you do when we get to quantum mechanics in about a month. It turns out that I am moving with a certain speed. Right? You're watching. I'm moving with a certain speed. But due to quantum mechanics, if I have a little bit more energy, I don't progressively speed up like that. What I do is my speed changes in discrete jumps. So I'm moving slowly, and if you give me more energy, I'll suddenly go faster. And if you give me more energy, I'll even go faster still. But there's these jumps in speed. It's not continuous. It's not that I'm slow and I slowly, kind of visibly speed up. My speed occurs in jumps. It's quantum mechanics that does that. So if you know what those jumps are, then you know what are the velocities to put into your sum. In other words, maybe it is, from like, if Vx is 0 to 0.1 to 0.2, meters per second, maybe it is like that. Okay. Now that probably sounds crazy, but here's the thing. You've seen that before. Now this is an aside. Maybe don't even write this down. But I want to remind you about you probably have seen this before. You should have seen this in organic class when you talked about isotope effects, right? So even in freshman chem, hopefully you saw something like this. You know that bonds are like little springs, right? So let's say we're doing oxygen, right? O2. Okay. Now, that has an average length, which is probably like about 1.2 angstroms or whatever, and it stretches like a spring. If it stretches too far, the energy goes up. If it gets too close, the energy goes up, and yada, yada, yada. Now, again, I'm hoping that you have actually seen a little bit about the quantum mechanics of how this works. There are quantum energy levels And again, you're actually going to solve this in about 6 weeks' time. You're going to do this problem, but hopefully you've seen it before. And what this means is that for oxygen, it vibrates with some ground state energy, and if you give it more energy, it does nothing. If you give it more energy, it does nothing until you get to a certain energy, a certain quantum energy, where all of a sudden it vibrates faster, right? It goes from the ground state to the excited state. And then you give it more energy and nothing happens. And then you give it more energy and nothing happens until you give it just the right amount of energy, and then it goes even faster. It goes goes from here, the ground state, to the first excited state, to the second excited state. But you have to feed it certain amounts of energy. And those energies, if you translate those to wave numbers, those are the peaks in an FTIR spectrum. And again, I'm hoping that you covered some of this in organic or maybe freshman analytical. You should have seen it somewhere, I hope. All right, what I'm telling you is translation works the same way. It's quantized. So you can know what are the correct steps in velocity such that you can do the sum. Okay, anyway, that's just a little bit of and I'm actually really just trying to preview a little bit of quantum mechanics. But now it turns out that these steps, and you're actually going to calculate it, by the way, it turns out these steps are really small. So what that means is that you can now, if you, I don't know if you've had this in calc class, this is not something that is normally covered in most first year calc classes. There's this thing called a Riemann sum. What it does is it's able to turn this summation into an integral. Now remember, integrals are the sums of areas like, okay, since I'm aside, right? Aside. When I do these asides, you don't have to necessarily write this down. It's not that important. But you remember Simpson's rule, right? You draw little rectangles over a function, and the integral is the area of all those rectangles, right? So what about that? Integrals are, oh, here it bothers me if I don't label everything. Okay. Integrals are the sums of areas, just like this little, summing up rectangles. So what Riemann sums do is that, you see I've got a sum here. It's not hard to turn that into an integral because integrals are just sums, right? Okay, now the way that works, and it works because the individual, like as you're adding in the Vx's, because the steps in Vx, like from 0.1 meters per second, 0.2 meters per second, because those steps are really, really tiny, that's why this works. Okay, and so the way it works mathematically is this thing is going to turn into this. Now, an integral, and the limits will be minus infinity to infinity, all right? That's not mind-blowing, is it? The function stays the same. And remember that most of these are just constants. And you plug in a partial. Okay, there you go. All right. Now I can evaluate this, and these other terms will of course be the same thing. If you're we're gonna do things like online, using online integrators, or using identities, and these other two will come out to be exactly the same thing, because Vx, Vy, Vz, that doesn't matter, right? Those are just labels. Those are just symbols. And if we were all Russian, we'd use a different alphabet. None of this would make sense anyway. So if I plug in a Vx to an integrator and do the evaluation, I would get the same thing if I plugged in Vy. So whatever this is, I'm just going to cube it, and that will be, let me say that again. Whatever I get here, I'm going to cube it. I'm going to raise it to the third power, and that will be what the whole thing is, the whole normalizer. All right, now let's do this part. Let me do an aside. Now again, I'm trying to prep you on your tests because you have to take tests, and I want you all to pass. The average for this class tends to be around 80, heads up. So if you get a 60, you're not doing good. Don't count on a curve. Okay, more about that later. We've got a couple weeks till, 3 more weeks till your first test. Now what I'm going to do is you better not be using your web browser during the exam, all right? You know what that's going to do. So I'm going to give you identities. I'm going to give you the way I do this is I'm writing the test, and then there's a question that needs an identity. I then Google it, and I'll give you the first thing that I find, the first thing that's correct. Right? Not that cool. I'll give you what I find on Google. I even like cut and paste it into the test, because that's what you're going to do, probably during the test. Anyway, all right, so here's what I find on Google. So I'm looking up an integral identity, and you can usually find these on Wikipedia. And that's usually what I cut and paste and put into your exam. Okay, so here's exactly what I find on Wikipedia. Integral identities. This right here. Okay. Now, here's all right, so we're at the test, and you have to evaluate this, and I gave you that identity. Now you've got to make it work. Now, hopefully you see that, like, yeah, this and this are real similar. Okay, that's good, right? Just that by itself, that's really good. Hopefully you recognize the limits, and you see you've got e to x squared. Here you've just got a vx, but again, symbols, right? If you were Russian, that it wouldn't even matter because they have a different alphabet. That this is vx squared and x squared is meaningless. The limits are correct, so this is my guy. I'll have other identities on the test. You got to make sure you get the right one. Okay, now then. Okay, well the answer is square root of pi over a. All right, so now what you got to do is figure out what a is here. And what I'm going to do is, all right, let me do my aside thing here. I'm going to say a. It's like imagine in your mind, imagine sliding this over here, right? And then you're looking at what a overlaps. That's a good way to think about this. And it looks like a is minus m over 2 kb t. And therefore, this integral is square root of pi over minus m 2 kb t. Okay, there you go. Right? You see how easy that is? And just like I said, I like to give you questions and answers that are wrong to see whether you recognize that I just did that, which is what just happened right now. This is not correct. I'm going to do this to you all the time. It's kind of fun for me. Anyway, what went wrong? What went wrong? All right, so where did we fail in our mathing? All right, for one, all right, big picture here. Recognize what you did wrong. All these constants are positive, but I have a minus sign, and I'm taking the square root of a minus. That means that this is an imaginary number. I don't think we should have imaginary numbers, so the minus is wrong. Why do I have a minus sign? I'm looking at this and I see minus x squared, and I have, you see what it is? You see what it is? Minus ax squared minus vx squared. The constant has a minus sign in front of it, so therefore the constant does not have a minus sign. That's external to the constant. So when I included it into the constant, I was wrong. That stands on its own because it's there. It's not part of A. So A does not have a minus sign. That's the same minus sign. There we go. And now that's the right answer. You see? And by the way, had you done that, I would have just taken off the point. It's a 10-point question. You would have lost just one. So, right. Averages are going to be cool. That would still be an A. So not too bad. But don't, you know what's better? Don't get it wrong. Okay, so there you go. I got the top, and now I can do the bottom, which is just this raised to the third power. So let me write that whole thing out, and let's see what we can do with that. I'll tell you what, I'm going to raise this up and wipe the board out. I'm going to wipe out the board, so I'll take a pause to the video so you don't have to watch me wipe out the board, and we're going to go from there. All right, everyone. So one of the benefits of doing all this online is that you don't have to sit here and watch me erase the board. Let's see here. Okay. So what is the now we're looking at the Maxwell-Boltzmann distribution. Let's see here. It is m over 2 pi kVt. It's flipped over because from the previous result, 2 pi kBt over m. Remember that the normalizer is on the denominator. So I'm going to flip it over. One of the terms is to the half, but remember I have to cube it. So the normalizer is now to the 3/2. Okay, so not too bad. Just don't forget that the normalizer is technically in the denominator of the Boltzmann equation. So when I have you work problems, if you want to be, if you're not confident, just leave it as a denominator. But to make it the expression a little bit easier to read, I flipped it over, and of course the remainder is just this. V squared over 2kBt. Right. So again, I flipped this over because it's just like a lot easier to read. It's like not as big. Okay. But, just like as I was saying just a little bit ago, you have to always recall that you're in 3 dimensions. So dvx, dvy, dvz. Okay. So we're almost there, but we've run into a mathematical problem that's unfortunately actually really quite bad. In fact, about half of the extra hour on Friday, I'm going to talk about how to deal with this problem. The problem is there's actually 2 of them. One of them is not that big a deal, but when you have 3 partials, you actually have 3 integrals, right? Unfortunately, multivariable calculus. Now, I know you haven't had that. I'm aware. So I'm going to cover the material that you need, which makes it legit. There's actually this one poor guy was going to go complain to the dean about how this class had multivariable calculus in it, and fine, but the problem is that I cover it, right? So it's valid, right? Besides, I'm actually going to get rid of this. Multivariable calculus, if you have 3 integrals, 3 partials, it's just 3 integrals multiplied. So that's as hard as it gets, so whatever, right? But I don't want to deal with this. I don't want to deal with 3 integrals. And there's even another problem. This is actually the real problem. I've got a v squared, and v squared has vx and dy and vz in it. But it's hiding, right? Because, let me give you an example. Let me make it a little bit more clear where the problem is. Okay, here's one of my asides, right? Okay, let's say we're integrating f dx from 0 to 1. You might say, well, that's f delta x from 0 to 1, which is just f. Correct. Unless f is really f of x, right? What if f isn't a constant? What if it's a function? Is this true? Is that true? Obviously not, or you wouldn't have even had a calculus class. You don't know what to do until you know what f of x is, right? F of x, if it's a constant, it's not hiding in x, but if it's a function, it is hiding in x. What if f of x is actually x, right? Then what you get is 1/2 x squared from 1 to 0, so that's actually 1/2. There you go. All right, so the point here being is that when I'm looking at this triple integral, and let's not worry about the multivariable calc, we're going to go over that stuff. It's not hard. And that's not a real problem. The real problem is that v, that net velocity, is hiding vx and vy and vz in it, and you cannot ignore that for the reasons I just explained here. Okay, now, there's 2 approaches to solve that. One is to turn v squared into vx squared plus vy squared and vz squared. We're going to do that on some practice problems. That is actually it's actually way easy. So easy, it's kind of not worth doing. It is surprisingly very easy. What I don't like about that is that what I really would rather work with is net velocity. Because I want to calculate like average net velocity. There's a lot you can do with that, including, remember how I said a minute ago, you can calculate the average pressure of a gas using using, sorry, I'm just going blah, blah, blah. If you tell me that I've got this O2 molecule and you tell me its mass and whatnot, I can use this mathematics to figure out what the average pressure is. Now, to do that, as you're going to see, you need to work with net velocity. So I'm not interested in making this go away. I'm interested in making this go away. I want that to go away. Now, how do I do that? I do that by the following procedure. What I'm going to do is divide it by the net velocity and then multiply it by the net velocity. Okay, now the trick is to evaluate this. How do you evaluate that? Okay. Now for one, hopefully you recognize that this actually looks kind of like a derivative. And that's the answer. It's kind of like a derivative. It's not that easy to work. In fact, you may recall, some of you math fiends may recall, this is called it's a Jacobian. All right. Now, Jacobians, I will show you exactly how to do this in the extra hour on Friday. It's also in the appendix of the little silly textbook that you have, if you really want to see it. I do have questions on the exam to analyze Jacobians, so that will be on the exam. However, I'm not going to make it as complicated. This three-dimensional Jacobian is kind of complicated. I want to show it to you, but I'm going to go ahead and tell you, I'm not going to put it on the test. I'm not going to put a three-dimensional Jacobian on the test. It's too hard. I will put a one-dimensional Jacobian. And the next, on Friday, during the regular hour, I'm going to show you a little bit about an easy way to analyze it using graphs. And then in the extra hour, I will then use explicit calculus mathematics to do it like the right way, but the hard way, unfortunately. Anyway. Okay, so this is how you're going to do this. And I guess actually at this point, before I get into it, why don't we go ahead and call it a day, because I think we've covered enough. And I told you I did not want to go a full 50 minutes because it's not really fair. I'm not able to answer your questions, and usually that takes up a good 5 or 10 minutes of a class. And we're going to have to, I try to do that during office hours. Try to email me questions, and I'll try to answer them during these lectures. If not, during office hours, we'll figure something out, right? None of this is perfect, and you know why. But let's see, just to end today's lecture, we're going to end a little early. This is what the Maxwell-Boltzmann equation looks like, but we have this slight problem of having this triple partial in x, y, and z, whereas what we really want is a net, the partial of the net velocity. It's going to be way easier to work with because then that partial of net velocity is right there, and then nothing is being hidden in terms of like that example that I stupidly erased. So that is what we're going to begin with next time, and we also have what I'm going to do is I'm going to release the first hour of class at 1 o'clock, and then I'm going to release the extra hour at 2 o'clock. It's technically backward from how I'm supposed to do it, but it actually will make a lot more sense if you watch it in that order. So that's how I'm going to do it. So, I will see you all on Friday.